This is Alan Elliott, and this is SAS Essentials, Mastering SAS for Data Analytics, 3rd edition. This is Chapter 16, Nonparametric Statistics. In this chapter, we'll be able to use SAS procedures to compare two independent samples using a Wilcoxon Mann Whitney test, to use a SAS procedure to compare K independent samples using Kruskal Wallis, to use SAS procedures to compare two dependent or paired samples, and to compare K dependent samples using a Friedman's test. Also, we'll look at performing a multiple comparisons test following a significant Kruskal Wallis test, and that will be in the form of a macro. As usual, if you'd like to follow along with the examples in this chapter, please download the files at this location. Thanks. Let's get started. This chapter is going to be about nonparametric tests. So there's an assumption for many statistical tests, such as the t-test and analysis of variance, that data are normally distributed. So when this normality assumption is suspect or can't be met, there are some alternative techniques for analyzing the data. Statistical techniques based on an assumption that the data are distributed according to some parameterized distribution, such as the normal distribution, are often referred to as parametric analyses. So statistical techniques that do not rely on this assumption are called nonparametric procedures. And this chapter illustrates several nonparametric techniques. So let's begin with section 16.1, comparing two independent samples using NPAR1WAY. So a nonparametric test can be used to compare two independent groups when you cannot make the assumptions associated with the t-test. The primary nonparametric test for comparing two groups discussed in this chapter is the Wilcoxon or Wilcoxon-Mann Whitney test. And the hypothesis tested is as follows. So the null hypothesis is that the two groups have the same distribution, that is, they come from the same population. And the alternative is that the two groups do not have the same distributions. They come from different populations. Now note how this is different than the t-test, which is comparing means from the two populations to see if the means are the same. And this is the distribution is the same. And also don't get mixed up into thinking this is a test that the medians are the same or something like that. That is not what's going on. All right, so let's take a look at PROC NPAR1WAY. This is the procedure we're going to be using to do these tests. And it looks very similar to what other procedures look like. We have PROC NPAR1WAY with some options and some statements. So some of the options include the data equal, but which is commonly used in all of them. But then we have some other options we haven't seen: Wilcoxon, median, VW, and we've seen no print before. And then some statements also for PROC NPAR1WAY. And again, we've seen some of these before, but the class statement, the var statement, the exact statement, which is not exactly the same as what we saw in PROC Freak, and then ones that are common by, format, label, and where. All right, our first hands-on example is going to be 16.1, and this example illustrates how to compare two independent groups using a nonparametric method. So in this, we have observations from two brands of fertilizers, and we're going to compare them to determine if one provides better overall growth, which is measured by height, than the other. Now, this is intentionally the same data used in AT-test2.SAS, which was discussed in a hands-on example in Chapter 12. So let's compare to see how these two different ways of looking at this data result in a decision. All right, so open up the program file ANPAR1.SAS. And we can see that we have the PROC NPAR1WAY. We have the Wilcoxon option here, which limits our output. If we don't have it in there, we get more output than we really want at this time. And the rest of it is should be pretty familiar to you. The class option is the brand, so we have the two different brands of fertilizer. And the height, the var height, gives us is what we measured, the height of the plants. We also asked for an exact test output to be given to us. All right, so let's look at these results. So the top table are the Wilcoxon scores, which is also called the rank sums, for the variable height classified by the variable brand. So here we have our brand A and B. Now we don't have means here. Instead, we have something called sums of scores. And then at the right-hand side, we have the mean score. So again, it's this test is not comparing means like the t-test did. We're comparing distribution. So let's look at the second table, the Wilcoxon two-sample test. And the results are actually given here three ways. So the results are either the Z two-sided p-value, which is p equal 0.0054, the T two-sided result, 0.0147, or the exact two-sided results, which is p equal 0.0025. Now these are slightly different results because they're slightly different ways of testing the hypothesis. In this case, they all have the same conclusion. So we would from these tests, all of these tests, we would assume that there is a difference between the two fertilizers. And then finally, the actual Kruskal Wallis test at the bottom is a chi-square test. And again, we get a p-value of 0.0045, which again agrees with all the tests above. Now again, why are there various tests? In this case, we'd probably go ahead and do the Kruskal Wallis test or the exact test, but there may be times when the other ones would be what you want to look at. All right, it also provides graphical results. This graph provides visual evidence of what we saw in the p-value. And again, it's always a good idea to look at a graph to, maybe even before you look at the p-value, to try to determine visually what's going on. In this case, we see that the heights for brand B were consistently higher than the heights for brand A. So we would sort of naturally then assume that brand B is a better fertilizer. In fact, the p-values then support that. Now let's look at, so that was two samples, so that was like a t-test. But let's now look at comparing k independent samples. That would be like this is sort of like an ANOVA. So if more than two independent groups are being compared using a nonparametric method, SAS uses the Kruskal Wallis test to compare the groups. And again, this is just an extension of what we just saw, but the null hypothesis is that there is no difference among the distributions of the groups. So we have three or more groups. And the alternative is that there is a difference between the distribution of the groups. All right, let's look at hands-on example 16.2. In this example, we're going to look at comparing three or more independent groups using nonparametric procedures. In this case, the data are weight gains of 28 animals that are randomly assigned to 4 feed treatments with 7 animals to each treatment type. So suppose we want to test whether there are differences among the effects of the different treatments. So if you have reason to believe that the normality assumption associated with the one-way ANOVA are not met, then you might want to do the Kruskal Wallis test. So this is the data that we're going to use for this analysis. Notice we have 4 groups, and each one of them has 7 pieces of data. And then down below you see the actual code used to enter this data, which the input variables are group and weight. All right, now open the program file NPAR2.SAS to do this example. And you notice it says we already created the data set called NPAR. So we're going to do a PROC NPAR1WAY, and again we use the Wilcoxon option here. Class group, just the same as we did in the previous one, except this time there are 4 group treatments in the group instead of 2, and that's what causes it to be this kind of test instead of the test just for the 2 groups. And then the variable, the one we measured, is called weight. All right, so here are the results, and notice the top table is called the Wilcoxon scores. We already saw a similar table. And here we have 4 groups, each with n of 7. And again, we have the mean score at the very right. Again, we're not comparing the means like we would in a ANOVA. We're doing something different here. We're comparing the sort of overall group condition or distribution. So these results show the rank sums as we saw here, and the test statistic is that Kruskal Wallis table, which again is a chi-square table. And here we have p equal less than 0.0001. And since this is since that's would be considered statistically different, we're going to assume now that there is a difference in the weight gain among the four groups. So it provides us with a visual confirmation of that. Again, always look at the graphs. And in this case, without even doing the test, you could probably clearly see that group 1 had the least amount of weight gain and group 3 had the most. Now what you don't know is 3 and 4 statistically different or not, or is 1 and 2 statistically different. We don't know that yet, but what we do know is that there is at least some difference in weight in treatment between at least probably 1 and 3, at least 2 of the groups. All right, so now let's look at comparing two dependent or paired samples. So two nonparametric tests for paired samples are available when in PROC univariate: the sign test and the Wilcoxon signed rank test. And again, the hypothesis for this would be, the null hypothesis is that the probability of positive difference is the same as that of a negative difference. So if we're looking at paired values, as we're going to see, and when we have a paired value, we can subtract one from another. If there's no difference, then we would expect generally 0 to be what we see there. But if there is a difference, it's going to be either consistently positive or consistently negative, that difference. So the alternative hypothesis is that the probability of a positive difference is different than that of a negative difference. So let's look at hands-on example 16.3. In this example, we're going to compare paired observations using a nonparametric technique. So in this case, we have a data set called weight, and notice we're inputting before and after, W before, W after, so this is before and after weights. We're also calculating W loss. W loss is before weight minus after weight, so that gives us how much weight someone's lost. And that's going to be critical in terms of what we need to do the analysis. So if you'll open up the program called aunipaired.sas, you'll see again, here's the code with W loss in there. And we point out that then that becomes the variable that we're going to use in PROC univariate, where we have the var W loss. So again, the weight loss is the value that we need to do this analysis. Not really directly the W before and W after, but we need that new calculated value, W loss. And then when we run this, we get this kind of table. And we actually saw this table or similar table in PROC univariate in an earlier chapter, but now we can use it in a different way. So notice here that actually a number of tests are performed in this. We have the student's t-test, which we could use if we assumed that this data were normally distributed. But we also have the signed test, which gives us a 0.07 p-value, and a signed rank test, which gives us a 0.0156 value. So notice here that we're getting a little bit of a different answer here. If we're using 0.05 as our cutoff criteria, then the signed rank test, 0.01, is less than 0.05, but the signed test, 0.073, is marginally larger than 0.05. So we would need to maybe take a closer look at this. Maybe we don't have enough subjects here to make a definitive decision here. So we have sort of a mixed results in this particular case. Now let's look at comparing k-dependent samples. And we're doing this, we're using something called a Friedman's test. So when the data include more than 2 repeated measures and the normality assumption is questioned, then we can perform what's called the Friedman procedure. And the null hypothesis is that the distributions are the same across the repeated measures, and the alternative is that they are different. Now there's no actual procedure in SAS, PROC Friedman's, or anything like that, but we can perform it by using a little trick using PROC Freak. So we'll see how that works. So recall that this data actually from chapter 13, in which 4 drugs were given to 5 patients in random order. So here we have 5 subjects, and then each subject was given drug 1, drug 2, drug 3, drug 4. They were given to them in random order. What we want to know is that is there any difference between these drugs? All right, to do this example, let's open up a file called afriedman.sas. And you can see here we're entering the data called time, and we're going to do a Friedman analysis. And we do a PROC freak, which is similar to what we've done before. Notice here we do tables, subject, by drug, by observation. So really a 3-way table we're asking for. The CMH2 option is asking for the Cochran-Mantell-Hansel statistic. And then scores equal rank, we're going to get the rank scores. So, and then no print means that most of the stuff that is going to come out we're not interested in, so we include that in the PROC freak options here. All right, so let's look at what does come out. And here again we see the Cochran-Mantell-Hansel statistics based on rank scores. And so the Friedman analysis, which is 14.125, with 3 degrees of freedom, and has a p-value of 0.0027. And because this is less than 0.05, we would conclude that there is a difference in the drugs, or a distribution across drugs. So here's a note at the bottom. The PROC freak statement requests a 3-way table, and statement options include the CMH2, as we mentioned here, and the scores equal rank option indicates that the analysis is to be performed on the ranks. The no print option suppresses the output of the summary table because it doesn't provide anything we need in this analysis. Now, in these tests, the nonparametric tests, SAS doesn't provide any multiple comparison tests directly, but we can do some, and so we're going to show you an example of how this might be done. So as in the Kruskal Wallis multiple comparisons discussed earlier, you could adjust your significance level using a von Ferroni technique. And for example, in the case of the 4 groups measured in repeated readings, we would perform 6 pairwise comparisons. Now this is discussed in the text, and I won't go into it more right here, but there is a way you could sort of do this using a von Ferroni technique. But we're going to look at a way to do this maybe a little bit more straightforward using a SAS macro implementation of a multiple comparison test called the NIMYAMI or Tukey type or Dunn's test, which along with the SAS NPAR1WAY, and there's a paper there mentioned there that you can look up the details about this test. All right, so to do this, let's open up the program called ANPAR3.SAS. And notice that what it contains is an include statement. Now we saw these include statements back when we were looking at how to create macros. So what it's doing is it's going to bring into this program a macro called KW_MC. It's then, because that isn't going to be necessary for us to do the analysis on this data. Now we're going to read in the NPAR data here, where we're going to be reading in group and weight, and then the @ sign again means that to continue to read this data until you run out. All right, so let's just take a quick peek at the macro. It's too long and too complicated to explain here, and again you can look at the paper if you want to see the details on how this is created. But here's a little snippet of it. We can see that we're creating a macro called KWMC, and we're entering several pieces of information: source, group, observation name, group name, and significance level. So I won't go into the details there, but you can look at that if you want to go through this macro. It's a good exercise to see what's actually going on here. Now let's call the macro. So we know that once we create a macro, we can actually call it, and we need several pieces of data to call it. This is the data that's going to be sent into the macro in order for it to do the work that we want it to do. First, we need to know the number of groups. In this case, it's 4. The data name is NPAR. The observation variable is weight. The grouping variable is called group, and the alpha level we're going to be using is 0.05. So at the bottom of this screen, you can see where we're calling the macro called kw_MC, and we've assigned all of these pieces of information. Notice the little and sign before each one because they're macro variables. So source is equal to and data name, groups equal and num groups, and all this sorts. So those are the things that we defined earlier. So that's how we call this macro to do the analysis that we're interested in. All right, so once we run that, we get some results. And what we're mostly interested in is the Kruskal Wallis test. So, and we see at the top of this slide, we see the Kruskal Wallis test with the chi-square degrees of freedom and p less than 0.001, which means, yes, we are finding that there is some difference between the groups. So the output for macro includes this multiple comparison test for these 4 groups. And notice in the conclude column, we have a reject, which indicates the comparison is significant at the 0.05 significance level, or do not reject means that it did not find a significance at the 0.05 level. For example, if you look at the first one, 3 versus 2, that's the first row in this table. We're comparing group 3 versus group 1. The difference in the rank sums, I believe that is 20.43, but we're going to conclude reject, which means that we're going to reject the null hypothesis, in this case, that they're the same, and we're going to conclude then that 3 and 1 are different. And so on, so forth, for all of the possible comparisons here in this table. All right, well, that's the end of this chapter for nonparametric analyses. The next chapter, chapter 17, is going to be on logistic regression. If you got something out of this tutorial, we'd appreciate it if you'd subscribe and like this tutorial, and we will see you next time. Thanks.